What's up everyone, welcome back. Patrick here, and moving on with limits at infinity. We got these four limits to solve here. And if you look at these limits here initially, they may actually look more simple than the limits we've been covering so far, than the examples in the previous videos. But there's going to be a lot of important stuff introduced in this video. There's going to be tools that I'm going to introduce that we're going to be using in future examples where the limits are going to get more complex. I mentioned that we're going to be dealing with square roots that are going to have multiple expressions, so stuff like this. But then they're going to get even more complex, where you're going to have multiple types of these expressions in like a numerator and a denominator. So, going to introduce a lot of tools in this video that will be used in future videos. Want to give a heads up. I'm also going to introduce a certain property. I'm going to do it actually after the first example, where the result of that property is going to be pretty important for this video and also future videos. So let's start with number one. We got the limit. Let's write it over here. As x approaches negative infinity of x to the power 5 minus 100 x to the 4. So you may be looking at this here, and you may be trying to sort of make sense of it in your mind. So what would happen if we plug in negative infinity for x? We'd have negative infinity to the power 5 minus 100 to the power of, or times negative infinity to the power of 4. And when you look at this, because this is to the power of 5 and then this is to the power of 4, we know that this expression is going to increase a lot quicker than this one. Even though this expression is being multiplied by 100, we know that one more power, right? So 4 plus 1, 5. This higher power here, we know that this is going to increase faster. So you may, just by looking at it from a higher level, be thinking that, okay, a negative large number to the power of 5 is going to give us another negative large number, right? Any negative number to the power of an odd number is going to give us a negative number. Then we got minus 100, and then we got a negative large number to the power of 4 would give us a positive large number. So we got a negative large number times negative 100 times a positive large number, which would be like a negative large number minus a negative large number, which would give us a negative large number. And that intuition would be correct. It's just, even the way I explained it, you may think like, that was a little bit kind of unsmooth, quote unquote. So how can we show this in a better way, that this limit here is going to equal this negative infinity without having to write all that stuff and explain it? You'll probably have to explain it in sentences to your prof, etc., etc. Well, what you can do here is you could take something like this and you can factor out the x to the power of the largest exponent. So notice that, what's the largest exponent? We got 5 and 4, so it's 5. So what would happen if I take x to the power of 5 from here, if I factor it out? Well, if I take x to the power 5 from x to the power 5, we're just left with 1. And then over here, we'll have 100 x to the 4 over x to the 5. Remember, when you factor something out, you're pretty much dividing everything that is left. So let's say I got 3x squared minus 9x, and I want to factor out a 3x. Well, whatever's remaining in this bracket is just these expressions divided by 3x. So notice the 3's cancel out. We're left with an x. And then 9x divided by 3x, that would just give us 3. The x's cancel out, 9 divided by 3 is 3. Right, so 3x squared minus 9x is the same as 3x times x minus 3. So whatever you factor out, you just divide the expressions by what you factored out, and you get left with that bracket. Same thing here. We took out x to the power 5, so we divided this by x to the 5, divided this by x to the 5, which I showed there. So this was just 1, and then we have 100 x to the 4 over x to the 5. So if we simplify this, we got limit as x approaches negative infinity. We got x to the power of 5. And then here we'd be left with 1 minus 100 over x. X to the 4 over x to the 5 just simplifies to an x at the bottom. It's like 4x is up top, 5x is at the bottom, meaning there's a 1x left at the bottom. And now what happens when we plug in this negative infinity? So we'll have negative infinity to the power of 5, and then notice here we'll end up with 1 minus 0. Because if you remember, a constant over x to the power of r, the r in this case is 1, limit as x approaches plus or minus infinity of that, that's always going to be 0. I introduced that property in multiple videos beforehand. So this would end up being 0 here. This would go to 0. So we would just be left with negative infinity to the power of 5 times 1, which would give us negative infinity. And so I feel like this way is a lot nicer to get this than the previous way, where we had like multiple negative infinities around, etc., etc. And this is actually a good introduction to a method that we're going to be using, where we're going to have to factor out that x to the power of the highest power in expressions, and a lot of times in expressions under a square root, right? Now, a result that I want to kind of go over here is notice that we ended up getting like negative infinity times a constant. And I want to show you, so let's say we have a constant that's greater than 0. So a positive constant. Can't be 0, can't be negative, it's positive. Whenever you end up having a result where you have infinity times that constant, that's going to give us what? Infinity. Right? A very large number times a constant, it's going to give us another very large number. What if you have negative infinity times that constant? Well, that's going to give us negative infinity. A negative large number times that constant, which is positive, is going to give us negative infinity. And if that constant is less than 0, if we have infinity times that constant, that's going to give us negative infinity, right? Negative constant times a positive large number is going to give us a negative large number. And if we have negative infinity times that constant, which is negative, that would give us positive infinity. So I want you to keep this in mind. I'm going to keep coming back to this result. And I also want to mention one thing. So we did when the constant is greater than 0, when it's less than 0, so when it's positive, when it's negative. What about when it's equal to 0? So I'll actually erase this. What happens when the constant is equal to 0? And we have positive infinity, we end up with positive infinity times the constant, or we have negative infinity times that constant, where that constant is 0. So we don't even have to write c, let's just write 0 over here. Well, we know that usually anything times 0 gives us 0. So does that mean that 0 times infinity would give us 0? Or 0 times negative infinity would give us 0? And the answer is no. So this doesn't hold here. And actually a good example of that, so remember this has nothing really to do with any of these limits. I'm kind of just showing you this separate property, but it is pretty important. I'm going to bring it up again in future videos. So to show you how this doesn't work, let's say we have the limit as x approaches infinity of, let's say, 5x squared over x squared plus x, like that. So we have a polynomial over a polynomial. And if you remember from the videos when we covered these kinds of limits, I mentioned that whenever you have a degree, the same degree in the numerator and denominator, and it's a limit at infinity, it's going to be the ratio of the leading coefficients. So notice it's 5 and 1, so 5 over 1 just ends up giving us 5. And if you were to show your work, divide everything by x to the power of 2, that highest power in the denominator, you could also do that. 5x squared over x squared gives us 5 over 1x squared over x squared just gives us 1. plus x over x squared, that would give us 1 over x. This would go to 0. We're left with 5 over 1. So we know this limit here is equal to 5. But what we can do with this function is we can actually split this up. So we can take 5x squared, multiply it by 1 over x squared plus x. Like that. This and this are the exact same thing. I just kind of took out this 5x squared. And notice if we plug in infinity here for all the x's, this would end up being infinity, right? 5 times infinity squared is infinity. And then notice 1 over infinity squared plus infinity, you'll have 1 over infinity, which would be 0. But notice now, we have infinity times 0. So if we treat this infinity like a regular number times 0, notice we would end up with 0 over here. But notice that that's not the correct answer for this limit, because we know that this limit for sure is going to equal 5, because we use tools that we've already made videos on that we're pretty comfortable with. We know that this limit is for sure going to equal 5. And so this is an example of where that infinity times 0 does not equal 0. So it can equal 0. It doesn't mean that if you get something like this, that the limit can't be 0. But it doesn't mean that it's going to be 0 for sure. So in general, a number times 0 is definitely going to equal 0, whether that's a positive number or a negative number. So, but you can't treat positive infinity or negative infinity like a regular number, right? And the reason why, just to dig into this a little more deeper since we're already here, is we don't know whether this bracket is going to go towards positive infinity quicker than this bracket here is going to go towards 0, or vice versa. We don't know if this bracket here is going to go towards 0 quicker than this one's going to go towards positive infinity. And that's why we can't really say that this times this is either equal to positive infinity or 0. We have to do more work. And in fact, what's going to happen is it's going to go towards 5. So anyway, thought I would mention that. This is going to come up in a future video. I'm going to have certain examples where we're actually going to run into this issue here. And we're going to have to bring in another tool to solve the limit. But thought I would introduce it in this video. So let's move on to the second limit. So we know this one was negative infinity. Let's kind of block that off. And then over here we got the limit as x approaches infinity of 4x minus 3, and what I'm going to do is this square root of x, I'm going to change it to be x to the power of a half. So same thing that we did here. What you want to do is you want to factor out the largest exponent, x to the power of the largest exponent, which is 1 in this case. 1 is larger than a half. So we got limit as x approaches infinity. Take out that x to the power 1. What would we be left with in the bracket? Well, we would divide this by x to the power 1, divide this by x to the power 1. So these x's cancel out. We'll be left with 4 here, minus 1/2 minus 1 is negative a half. So this here would end up being 3 over x to the power of a half. So now, notice we could do a substitution. So x to the power of a half, if we sub in infinity for x, we'll have infinity, or sorry, x to the power 1. So we'll have infinity to the power 1 times 4 minus 0, because this is going to go to 0, a constant over x to the power of a rational number. As x goes to positive infinity, we know that that's going to be 0. So notice we have infinity times a number, which gives us infinity, positive infinity. So number 2 is equal to positive infinity. So that's how you can show your work. Number 3, this one's going to be a little different. And this is a pretty important one because it's going to introduce a process that we're going to be using in future videos for more complex limits. So we got the square root of 2x squared plus 1. So how do we do this? How do we show our work? What you want to do here is you want to do the exact same process, but under the square root first. So let's say we had 2x squared plus 1. What we were doing was we were factoring out that x to the power of the largest exponent, which is x to the power 2 in this case. So if we factor out x to the power 2, divide this by x to the 2, divide this by x to the 2, we'd be left with 2 plus 1 over x to the 2. Like that. So 2x squared plus 1 is the exact same as this, x squared times 2 plus 1 over x squared. And so we're following that exact same process, except now that factored expression is going to be under the square root because there's a square root we got to deal with. Like that. And what you want to do here is you actually want to split these two up with their own square root. So if you remember, if we're taking two things and multiplying, like square root of a times b, that's the same as a square root of a times the square root of b. And notice we're multiplying two things. We're multiplying x squared by this entire expression, 2 plus 1 over x squared. So what we're going to do is we're going to have square root of x squared times the square root of 2 plus 1 over x squared. Just split up that square root. And then we could simplify here because notice that x squared, the square root of x squared, is just x. So whenever you have, so let's rewrite this. X squared, that's the same as x squared to the power of a half. And whenever you have something like this, you just multiply the exponents there. So 2 times a half just gives us x to the power of 1. And it doesn't necessarily have to be the square root. It could be the nth root of anything. So basically, whenever you have like the nth root of x to the power of a, that's going to be x to the power of a over n. So let's say we had like the third root of x to the 12. That would be like x to the power of 12 over 3. 12 over 3, which would be x to the 4. Right? Just a little review of exponents. This is going to be important. We're going to be using this. We're going to be using that in number 4, because notice we have a third root instead of a square root, and in future examples as well. So the square root of x squared is just x, and then this here, let's just leave it. We got 2 plus 1 over x squared. And now notice we could plug in infinity. So if we plug in infinity here, we got infinity for the x. And then if we plug in infinity here for this x squared, we got 1 over infinity squared, which is 0. So we'll have the square root of 2 plus 0, which is like infinity times the square root of 2. So we have a constant times infinity, which, as I mentioned before, is just equal to infinity. Right? So that's the proper way to show your work for this, instead of just plugging in infinity over here. Right? You always want to get to the point where you have infinity or negative infinity times some kind of constant, where that constant is not 0, some kind of real number. So number 3 ends up being positive infinity. That is the answer for number 3. And then finally, number 4, exact same process that we did in number 3. So if I rewrite this, I'll have the limit as x approaches negative infinity in this case. We got the third root of negative 5x to the 6 plus x squared. So same thing. What you want to do take this expression. Sometimes before you get comfortable maybe doing this, you could take these expressions, sort of write them on the side, work with them without the square root bothering you. Factor out an x to the 6. We'd be left with what? Negative 5. Those cancel out. And then x to the 2 divided by x to the 6, that would end up giving us 1 over x to the 4. So this here is the exact same as negative 5x to the power 6 plus x squared. So rewriting that in the square root, under the third root rather, we got negative infinity, we got the third root of x to the 6, then we got negative 5 plus 1 over x to the 4, like that. And then what we do, like we did before, is we split up the third root. So we'll have the third root of x to the 6 times the third root of negative 5 plus 1 over x to the 4. Now, the third root of x to the 6, that's like x to the 6 times 1 over 3, which gives us x to the 2. So this here would end up being x squared, this expression. And then this expression, let's just leave. We got the third root of negative 5 plus 1 over x to the 4. This is still limit as x approaches negative infinity. So what's going to happen now? If we plug in negative infinity for all the x's, we'll have negative infinity squared times, this is going to go to 0, 1 over x to the 4, so we'll just be left with the third root of 5. And notice negative infinity squared is going to give us positive infinity. A negative large number times a negative large number is going to give us a positive large number. And then this is just a constant, the third root of 5. So the constant times infinity, that just gives us positive infinity. So the answer to number 4 is positive infinity. And we're going to be using this exact same process with more complex limits where we're going to have multiple expressions like this in both the numerator and denominator. And we'll cover that in the next video.